Yeah. Okay. Thank you everybody for having me and Lynn, Professor Lynn Kaminsky in particular, for having me continue being involved in the program. I'm really enjoying this, and I hope, and the interns that I've had so far have been great, really great. So I'm going to share slides and jump into my talk immediately. Uh, Yeah. So the first slide is actually to talk about one of the two students I've had this past year with the N3 program, Finn Braun. This is the only slide that will be dedicated to work he's done. I'll talk about Krista's work in a later in my talk, but with Finn, we've been looking at the immediate return to the moon that NASA is focused on right now. And I don't know if you followed the news, but it was just announced a few days ago that three groups of US industry partners have been selected to continue their design and development of a potential little lunar rover, a two-seater, for future astronauts on the moon. And so the lower left diagram shows you the three vehicles that are now in competing as finalists for what might end up being the next generation lunar rover that astronauts can drive around on the moon while wearing a spacesuit. Uh, JAXA, the Japanese space agency, is taking care of developing a pressurized rover. So that's a bigger rover, more like an RV, in which you would live in shirt sleeves. You'd put on a spacesuit to go outside, of course, but otherwise inside you could sleep, work. And so Toyota and JAXA are working together on this. And of course, uh, uh, it's sort of not only a division of labor, but a division of cost. So we're trying to spread the cost of returning to the moon amongst the various international partners. But Finn's study with me this year was to try to design a little lunar ATV. So that would be a single astronaut transport. And I'm not showing you the design that we are working on right now. Finn will be presenting that at an upcoming conference here in just a few weeks in LA. Krista is going there too to present her work. So I'll save Finn's concept vehicle for later. But today I'm going to talk to you about, yes, this discovery of an ancient, deeply eroded, and possibly still active giant volcano on Mars. It's hard to believe that 50 years into the exploration of Mars by robotic spacecraft, during which there has been continuously pretty much orbiters around Mars taking pictures, looking at the whole terrain of the planet, that somehow there were still things like this that were still left to be found. To be fair, this is a very deeply eroded volcano. You're looking at it in this picture. You're looking at it. You can probably see that it has this roughly circular structure to it. But I'm going to show you in the next slide the overall outline of it. And here it is. This outer circle is the base of the volcano. Everything that is within this circle is rising towards the summit area. The actual crater, lava lake crater that once occupied the central region of this volcano is marked by this little pink dot. Uh, but you can see that the slopes of this volcano are very shallow. You can hardly tell that you're even climbing in most places, but you are. And in fact, the coloring of the topography tells you that as you go higher, the terrain turns into this white terrain, which is marking the highest elevation points in this region. The volcano's summit is at 9,022 meters. That is higher than Mount Everest from sea level. So it's a remarkable structure. If you see at the bottom of the picture, there's a little dark blue notch. That little notch is like a pit. That pit elevation is minus 700 meters. And so from that pit to the summit of the volcano, the white patches above it, you have a change in elevation of almost 10 kilometers, 10,000 meters. That's close to 6 miles. It's quite incredible over a distance of just about 150 kilometers, so about 100 miles. Okay, so you drive from the dark blue pit there to the highest elevation white areas. You have a distance to traverse of only 100 kilometers, but then you've climbed close to 6 miles in elevation. So, of course, what's obvious and noticeable in this volcano is that it's deeply eroded. It's missing a lot of parts. It's missing the foreground part, which is very low in elevation. It's all gone. It's missing a number of these areas that are now canyons amongst these little islands of plateau that you still see forming the center of the volcano. But yeah, we found a giant volcano on Mars. So let me get into it quickly. First of all, the way we got even started in it being interested in this area came from a workshop that NASA organized in 2015, before some of you were born. Maybe not. Well, close. And this workshop was calling for scientists and engineers to come together to propose possible or their favorite future landing site for humans on Mars. It was a historic workshop. It was the first time that NASA ever invited people to propose landing sites for humans. There had been many workshops for people to propose landing sites for robots, for rovers, for landers, but not for humans. And so to me, that was a very historic event. It marked the notion that going to Mars was becoming serious in the minds of people in management at NASA. And so it was a very good sign. Now, here were the constraints. Thou shalt not land at latitudes that are too far north or too far south. So the latitudes, in other words, the regions of the planet that are beyond 50 degrees north or 50 degrees south were off limits. That's why they're sort of darkened. The reason why those are off limits is because it's too cold. And in the winter in these areas, the temperatures are way too low for electronics to be happy. And also, it's dark. The seasons are the daylight is very limited. And so why go to such extreme places when you can enjoy more balmy areas on Mars? And then another whole category of terrain was off limits, which were terrains that were too high in elevation. So everything that is grayed out here in the middle of the map is at plus 2 kilometers. That's considered too high. Plus, in other words, higher than 2 kilometers above average Mars. That's considered to be too high. Bear in mind that when you land on Mars with a rocket or a rover lander, you have to use the atmosphere to brake, to slow down. And so your heat shield is used for that, but that's not enough. You're still traveling too fast. And so you have to deploy parachutes once the atmosphere gets thick enough. And then the parachutes are going to slow you down, but still not enough. And you have to fire up retro rockets at the very final end of your descent to have a smooth, soft landing. And you can imagine that you need a lot of height above ground to make all this happen. If you are trying to land at an elevation that's too high, you don't have time to deploy, to slow down, basically, until your retro rockets are in use. So no landing above plus 2 kilometers. So 50 groups came together independently, proposed their favorite landing site. I led a team that proposed Noctis landing. I've circled it. But you can see how people were interested in going to all kinds of places on Mars. I liked, and my teammates liked Noctis landing because if you drive east, you go into the giant canyons of Mars. And if you drive west, you start climbing onto these giant volcanoes, which you see as huge zits here on this map of Mars. And the giant volcanoes are exciting because they have caves, And inside the caves, we might actually have a chance of finding life on Mars that's still alive. We don't think that there's going to be life on Mars that's still alive today at the very surface of Mars. But if you go underground, you might have a chance of encountering environments that are sheltered from radiation from space, radiation from the sun, super cold temperatures, micrometeorite bombardment, uh, the super dryness of the surface as well. So things might be a lot more pleasant underground on Mars. And of course, to go underground, there's two ways of doing it: the hard way, which is to drill, and then the easier way, which is to, well, nothing's really easy, but the less difficult way, which is to go into a cave that already exists. And so, but going back to the canyon part first, if you drive east into the canyons, some people, of course, have been proposing that you could just land like, the Coprades Chasma landing site, or the what is it? The I mean, there are various canyon landing sites to the east of where we proposed that are really spectacular. But the problem with landing in these places, in my view, is that, well, let's say you land on the floor of this canyon. Well, then you have all these rock layers that are above you. How are you going to reach them? I mean, are you going to go mountain climbing? And, it's really challenging. The depth of the canyon that you see here is close to the height of Mount Everest. It's huge. So even though you would be very close to the canyon walls, you're not necessarily in a very good place to study them. Whereas where we're proposing to land, which is this area called Noctis Landing, it's a relatively low and flat area. Well, thankfully, it's actually right in the eastern end of these giant canyons. And thanks to this impact crater, this ancient impact crater, so that was formed by an asteroid or comet that hit Mars, called Oudemans, that you see south of where we want to land. Thanks to Oudemans basically managed to break up some of the canyon wall sections and laid them flat for us to explore. So this is a picture here taken from space in orbit around Mars, where you see the canyon walls of the Valles Marineris Canyon all laid flat so that you could drive from one rock layer to the other. You don't have to do rock climbing to study these rock layers, and they're all kept in sequence so that you know which one came first, which one came second, etc. Still, so these are the types of strategies that, as a field geologist, you would want to think about. It's not just a matter of being close to the things that you want to see. You have to be in a good spot to really be able to examine them and access them. So access is really critical when it comes to thinking about field work on Mars. And then if you drive west to the giant volcanoes, these are the caves I'm talking about. This is a hole in the ground on the flanks of the volcano, of one of the giant volcanoes that you saw out west. And this opening in the ground is 150 meters, so that's about 90 150 meters. Well, that's more like close to 500 feet across. Okay, and about 175 meters deep. Okay, so close to 650 feet deep. And in fact, it's more than that because we don't know how deep it is. No amount of image processing brings up the bottom of this pit. I call it the bottomless pit, but it actually has a name. It's called the Jeanne Pit, and it's on Arsia Mons, which is one of the giant volcanoes of the area. Well, after the workshop, NASA did not tell us which side it liked, which side it didn't, but it clearly was favoring the sites that were higher in latitude, closer to the North Pole or the South Pole, as opposed to the ones that were near the equator, like the place we proposed. And that's because they added the extra criterion that we should be able to land next to water ice so that we could extract water ice, use it as a solvent, use it as something to hydrate your bodies, to drink. So you melt, you process the ice, you melt it, you drink it. And also because water ice, water H2O can be broken down into hydrogen H2 and oxygen O2, and those put together are rocket fuel. So it's therefore very advantageous to be able to access water on Mars, because now if you can make fuel on Mars and also drink water from Mars, you don't have to bring these things from the Earth, and then you can travel much lighter. It can be much cheaper to go to Mars. So this is a map showing you where we think water is near the surface on Mars. Everything that is sort of a deep blue here is water that is very close to the surface of Mars within the top 1 meter. In other words, the top 3 feet of the Martian surface. The areas that are light blue, if they are far north or far south, yes, they are also due to water. But if they are near the equator here, that's something different, because this is technically not a map of water. This is a map of hydrogen. The thinking is that hydrogen is most likely found in the form of, a constituent of water. And so therefore, if you map hydrogen, you are in some sense mapping water. But near the equator, for example, these light blue regions are actually not thought to be due to water ice that's near the surface. They're thought to be due to hydrogen that's inside the minerals of the clays and the soil of Mars. So you got to be careful how you interpret this. But bottom line is, the farther north or farther south you go, the more ice you're going to encounter near the surface. And so this type of need to find water ice was pushing NASA to consider, not landing where it gets too dark and too cold, but at the same time still near the boundaries of the northern or southern regions. So that was a bummer for us. But we nevertheless, and this is maybe a lesson in perseverance, we nevertheless explored our area as if we had landed there and really wanted to check out what it offered. And sure enough, the black dot here was the originally proposed landing site. The light blue dot is where we found an ancient glacier, the remains of a glacier. And we think that there's still ice there, just to jump ahead of the story. So here it is. You can't really tell if you're not really trained to, look at glaciers that are dying. But here's the glacial tongue. And this is still not enough to convince you, I'm sure, because that's not what convinced us. But if you look at the highest resolution pictures, like this one, all of a sudden you start, and of course you process it properly, you start seeing all the crevasses, the features that are all very specific and typical of glaciers: moraines, thrust plains, foliation, which is the swirling, if you will, of the ice when it flows downhill, the tongue-shaped front of the glacial tongue here, like here. Anyway, this is the annotated version of this picture, showing you all these very characteristic glacial features that you can see there. Now, you're not looking at ice. Even the light blue here is not actually ice. The light blue is salt, not table salt, but a sulfate salt called jarosite. And so that's really weird, because now you're looking at a salt deposit that seems to look exactly like a glacier. So how could that be? Well, the solution, I think, is provided, we think, because I was working with my student intern, Surab Shubham. Surab and I think that the light colored material here, the brownish stuff, is actually a volcanic deposit, not lava. There's lava here in this picture. It's the dark black stuff on the far right. But the reddish brown stuff is volcanic ash. And here is the beauty of this finding. When you have a glacier, let's imagine you have a glacier there, and then there's a volcanic eruption on Mars that blankets the glacier with volcanic ash. You have a chemical reaction that's going to take place between the ash and the ice. And guess what is produced by that chemical reaction? Yes, salt, and specifically sulfate salt, jarosite, which is the specific mineral we're talking about. So this was from our perspective, a real nice confirmation that indeed we're looking at what are the remains of a glacier. And in fact, the what we think happened here is that the blanket of ash material got eroded, but not so deep that it removed the salt underneath it. And beneath the salt, we think that there's still ice. And we think that there's still ice beneath the salt because otherwise the salt would have completely crumbled and not preserve all the fine texture and features of the glacier ice. But we're not sure. That's what we think happened here. And so if you go land here and dig through the salt, at some point, not very far down, maybe 1 or 2 meters deep, so 3 to 6 feet, chip away at the salt, you should find ice. And so this would be a very exciting thing because, as you know, now we're near the equator. I mean, this is a place that you saw where we were on that big map of Mars. We were near the equator, and now if near the equator you can find ice still, and that's really great. So just to show you a few more details, on the left you have our Mars relic glacier, and then on the right, a dying glacier from Iceland at the same scale where you see very similar sets of features. And then these are other types of crevasses that we see in this relic glacier that you find in associated with glaciers on Earth as well. So traveling the Earth, exploring our own planet helps a lot to recognize things that we're sort of trying to interpret and see on Mars. You got to be careful though. Just because it's a lookalike doesn't mean it's the same thing. But when you have a wide range of independent observations that sort of converge towards the same conclusion or the same likely interpretation, well then that's how you build a case for what this might be. Anyway, this is the very highest resolution imaging that we have of this glacier. And you can really see the fine scale texture that are preserved here. So I would so love to land there and check out these crevasses and chip away at the ice, at the salt first, and then maybe at the ice. Now, this idea that salt can protect glaciers is actually proven on Earth. This is now in Bolivia. What you're looking at is a salt lake. Some of these white islands in the salt lake are actually icebergs. Icebergs that are still preserved from, we think, the last ice age. So some of these chunks are at the very least hundreds to possibly a few thousands of years old. The ice age lasted well into just a few thousand years ago in Bolivia at high altitude. And the icebergs are still preserved because they're completely blanketed by salt. The salt is very highly reflective, so it keeps the ice cold. Sunlight is sort of reflected away. And the salt is thermally insulating, so it literally acts as a blanket to protect the ice from melting away very quickly. And in this case, it's not table salt nor jarosite like on Mars. It's yet another type of salt. It's borate salt here, but it's the same idea. The same idea, salt protecting ice. So here you have some of these ice islands that are still preserved in Bolivia. So I'm trying to put together an expedition. Well, that's a big word, but I don't want to call it a trip. So I'm calling it an expedition to Bolivia to check these things out. And we're looking for funding, but we're trying not to have to write a big, long proposal for that. It's just a quick trip to go check out these ice islands. But we're not there yet. Anyway, for this year, so this finding of the glacier was last year. For this year, we were going to just report the fact that, hey, outside of this glacier, which you see here with the, near the tip of the long yellow arrow, outside of this glacier, well, we see all kinds of these other weird-looking mounds and pits that seem to be covering this entire region. And sure enough, we think that what's happening here outside of the glacier, with this terrain that we describe as blistered terrain, you can see that all these little mounds with a pit at their top, look like busted blisters that you have on your skin. I mean, I hope you never got blistered this bad, but we're calling this blistered terrain. And we think that blistered terrain actually, in this case, so blistered terrain is just a description of what it looks like. The geologic interpretation of what it is, or what it could be, is that these are rootless cones. In other words, steam bubbles that burst. So think of the hot ash coming down on this whole area that was somehow blanketed with ice. The hot ash comes and sits on the blanket of ice. The ice is going to sublimate, turn violently from ice to vapor because the atmosphere is so thin on Mars, it doesn't have time to really melt. It just goes straight to vapor. And so all of a sudden, the ash blanket is going to rise because there's steam building up underneath it from the ice turning into vapor. And at some point, these steam bubbles burst. And you have this type of landscape called rootless cones. We see rootless cones in Iceland, for example. They look just like this. In the case of Iceland, it's actually lava flowing onto like a marsh or very water-rich ground. So that's when the steam busts through the lava flow. Here we think it's actually ice steam busting through an ash deposit. Okay, but the story there though is that every one of these blisters is telling you that there could be still a lot of ice underneath this blanket of volcanic material. Okay, and so we mapped out all these blisters around the area of the relic glacier we found last year, and it turns out to be 5,000 square kilometers. So I have no idea what that is in square miles, but ballpark, I think 3,000 square miles, something like that. It's huge. This huge area of blistered terrain could be still protecting a sheet of ice that big. Now, we were just going to publish that this year at our conference there in Houston in March, when Surab and I started wondering, well, wait a minute, we have to try to figure out where all this volcanic material came from. First of all, the ice is not, for the ice to still be there, the glaciers that we're talking about cannot be very old. And you don't see a lot of impact craters covering all this terrain, so it hasn't been exposed to the elements of asteroids and comets crashing on Mars for a very long time. So the ice is relatively recent. And the volcanic blanket on top of it, the ash deposit we've been talking about, has got to be even younger. So where's the volcano? And then next to that glacier, you also saw, remember you seeing that dark lava flow? That's a pretty fresh looking lava flow. Where's the volcano? So we started zooming out from this area, and sure enough, already now you can see the ancient lava lake, one of the ancient lava lakes at least, of this volcano at the upper left of this picture, right under the word volcano ice. You can see that round flat area. That's the ancient lava lake in the center, at the center of the volcano. Okay, and you should bear in mind that a volcano doesn't just erupt at its center near the summit. It also erupts off to the sides, and so we don't think that the ash deposit came from the summit necessarily. But the point is, we wanted to find a volcano, and sure enough, we found something really huge. And in fact, the ice deposit at this point is inside it, inside the volcano. So by zooming out, we started looking for high points. What is the highest in the terrain, in the landscape, etc. And I'm going to move fast here just to get to the bottom of the story. But here you're seeing only the high points in this region. Everything that is in black and white is lower in elevation, below 8,000 meters. Anything that's higher than 8,000 meters is shown in color. And you can see that there's not a lot left. But there's this arc of hills in the middle of this picture here, where the highest points are in the browns and whites colors, and then as it slopes downhill, you get into the orange, the yellows, the greens, and the blues. And you can see that the slope is sloping downhill towards the north. For the northern patch of color, it's sloping towards the southwest for the southwestern patch, and it's sloping towards the south for the southern patch. So you have the remains of a cone, and that is really what gave away the this gigantic volcano for us. You have the remains of a cone. Okay, that lava lake that I was mentioning to you is right above the number 9 at 9,022 meters. It's actually not very high in elevation, but it's smack dab in the middle of all this sort of cone. And if this is if this cone or the remains of a cone is the remains of a volcano, you can see how much of it has been lost and eroded away. So this is a zoom in on the lava lake, so to speak. Of course, it's not lava anymore. It's just, uh, you know, well, solid lava. Okay, it's not molten anymore. With the highest elevation terrain right next to it. Now, if you zoom further out, you see that this volcano, which is pointed at by the white arrow, well, I shouldn't call it volcano. Well, yeah, I'll call it a volcano at this point. It's actually sitting on this very broad regional rise called the Tharsis Rise. The three giant volcanoes that are shown near the top of this picture are the very well-known giant volcanoes of the Tharsis region. There were no giant volcanoes known in the eastern part, which is where the white arrow is. So this is a weird perspective where west is at the top, east is towards the bottom, and north is to the right. But anyway, you can see that the giant volcanoes that were well known are all riding on this general regional bump in the crust of Mars. And this bump in the crust of Mars comes from, we think, well, not just we, meaning Surab and I, but previous scientists have hypothesized that this bump in the crust of Mars is from a plume in the mantle of Mars pushing upwards on the crust. Anyway, it resulted in fracturing of the terrain and in further erosion of our volcano, we think. So just to point out that our volcano, we're not dreaming it, is really a high point regionally. We are showing you some sections here. If you go from A to A prime, or B to B prime, or C to C prime, here are the profiles of of the elevation of the terrain. And you can see that the central part of the volcano sticks out like a sore thumb. It rises well above the regional hump that this Tharsis rise produces in this region. And at the very bottom, I show you the A to A prime profile with projected on it Mount Everest as well. If you go from Tibet in the north through Mount Everest and then towards Nepal in the south, that is to scale the change of elevation that you encounter. And that is actually just about what we're seeing here with all these canyons and high points inside this volcano, just to show you how deeply eroded it is. All right, as far as the actual width of the volcano, we talked about its height, its width. Well, we think that it's about 450 kilometers wide. Okay, if you go all the way out to those distances and you walk uphill, you are still heading towards the summit of the volcano. Beyond that, you might end up walking towards the Tharsis Rise, not necessarily the volcano, but there's a clear break in slope that's associated with this volcano all the way out to about 450 kilometers, well, at least in diameter. So that's what we think is roughly the size of this volcano. I'll just say briefly that we know that this volcano has to be very ancient because the fracturing that you see here has been analyzed by other scientists before. They think it's very ancient. I'm hearing somebody talk. Is that telling me to wrap up?
I did not hear anything. It may just be some background.
Okay. Okay, I'll just ignore. So yeah, the fracturing we know is ancient, but meanwhile, if you notice, if you look carefully, the fracturing actually wraps around the volcano, and that is telling you that the volcano was there before. So we're very excited about publishing this very shortly, although we've sort of described that a little bit already. So the volcano started first, and then the crust fractured, and sure enough, the fracturing went around the volcano. There are many examples on Earth where that has happened. If you fracture a region where there's a pre-existing volcano, the fracture lines are going to go bend around and wrap around it, which is why we think you have all these curved canyons around, circling the volcano. So this is it. This is the overall structure. The outer diameter is 450 kilometers, the inner one 250. Um, the relic glacier is that little thumb-shaped white patch towards the lower right. The summit is actually the white triangle. That's 9,022 meters. The middle of the frozen lava lake is marked by the cross, and then the outline of the sheet of ice is shown there as well. So this thing is big, very ancient, deeply eroded, but because the volcanic material, the ash and the lava flow that are next to the relic glacier are so young, this is a place that must have been active for a very long time, including recently. So this is what's so exciting, I think, scientifically about this place. Is not only do you have a volcano that's very ancient, but it seems to have been active even in recent times. And so you're looking at a place that has been thermally a source of warm temperatures throughout Martian history, and on top of that, involving ice and water being such an important ingredient in for life, that this is becoming a very exciting place to go search for signs of life, past or present. So our original landing site has now been moved, thanks to Krista Heinemann. That was her project, to try to find us a landing site that was closer to the glacier, as close as possible, in fact. So before I show you where she is suggesting we land, I'm gonna just show you here that the volcano over time was also eroded by glaciers. So it's not just the notion that there was faulting going on, but the glaciers actually created all these notches that you see on the sides of these mesas. This is also very characteristic of glacial erosion. So here's sort of a brief summary of the history of the volcano. And of course, this is actually a 3D animation or rendering that I stole from the internet, but so shouldn't publish this recording of this talk, but just to illustrate the idea, you have an original volcano, which in this diagram at the top was probably layered. It had layers of ash, layers of lava flows, which are shown in dark, like almost black, and then lots of layers of ice from just water vapor getting coughed out of the volcano and draping the landscape once it reaches the very cold atmosphere of Mars. And then as the volcano is riding on the Tharsis rise, and the rise pushes up, that whole regional hump, as it gets pushed up, the terrain gets fractured. And these are dark, thin lines that you see that are bowl-shaped around the section of the volcano. These in turn became conduits for lava to rise. And so once lava started rising off to the sides of the volcano, it would have melted or vaporized as well the ice very dramatically. And the ash layers and the volcanic layers that were so nicely organized before would just collapse into a jumble. And so you end up with these circular canyons that go around this ancient remnant of the center of the volcano. A few more eruptions later, a few more glaciation later, you end up with basically the current situation, a deeply eroded, collapsed volcano. And you can see this mix of lava flows and ashes even in some of the better exposed edges of these cliffs that we see within the area of the volcano. In the image on the left here, the massive bluffs, these very hard-looking cliffs, are made of lava flows, we think, very strong rock, whereas the very thin layered bedding that you see above the lava flows, we think are made of ash deposits. I mean, that's exactly what they look like, at least on Earth. So this is a volcano that has been erupting a mixture of things, not just lavas, not just ashes, but a combination of both, depending on when. And we still think that there's plenty of ice inside the remaining mesas, these remaining blocks of the volcano. If you look at the diagram here at the bottom, which is sort of the modern phase of this, there's still ice inside some of these, uh, mesas. These mesa is a Spanish word for table, and it just means a flat top, hill. So you can see there's some flat top hills there that are isolated now, and they have water ice in this model still inside them. And we think that's precisely what we're seeing here. You have the edge of a mesa here in the foreground. An impact crater just took place. It's very fresh looking. It's relatively recent. And it created a little splash pattern near the surface on the top of the plateau. But since it hit the edge of this mesa, it also apparently mobilized a huge amount of ice that was buried underneath the mesa. And you can see this gigantic fan-shaped deposit that expands towards the right of this crater into the canyon floor. That we think is due to ice getting kicked out, if you will, from the edge of the mesa. Now, in addition, people have identified hydrated minerals. So these are minerals that involve liquid waters, relatively high temperatures, interacting with volcanic materials. And so before we even found this volcano here, these little dots, colored dots, were findings by other scientists telling us that, hey, this is a region where there has been quite a bit of heat and water involved together to form all these mineral deposits. Surab and I added a few of these colored dots, but most of them were from previous studies. And sure enough, here's the volcano. So that's it. In summary, you can see the three giant volcanoes of Tharsis in the far left, which were known before. This thing, the red circle is actually the actual base, the size of it, is now the new kid on the block, although it's a very ancient volcano. We propose a name for it, Noctis Mons. It hasn't been approved yet, but the process of approving it is in the works, or rejecting it, we're not sure. But it just, Noctis Mons means the mountain of the night, like day and night, mountain of the night in Latin. And so this is sort of a perspective view summarizing some of the things we've talked about, but the new landing site that Krista Heinemann has been proposing is shown here, Noctis Landing. That's that oval area. It's near the Relic Glacier, it's near the dark lava flow, it's near the rootless cones, it's near the pit. Remember that dark blue notch that had an elevation of minus 700 meters? That's actually called the Pink Panther Pit. And it's right there in the foreground on the left, all the way to the summit of the volcano that you see there in the middle near the top. So this is it. As Krista's name mentioned, this is the proposed new landing site, which is nice, flat, smooth, a bit duny. It has more sand than we would like, but with some skill, you should be able to land there. I mean, I'd go in a heartbeat, and I hope some of you would. Here's a zoom in of this area. So you see that, the darker patches, okay, are the smoother, flat areas. The light yellow is actually very duny. The darker areas are, you've got two kinds of dark areas. The pretty rough looking dark areas are actually volcanic lava flow remains. So you don't want to land on that. It's pretty rough. But the smooth dark areas are where we think we can land. It's a little duny, but not too much. The bright yellow smooth areas are really duny, and you don't want to land there. But you can see that there are still clusters of hills here, as opposed to some big, wide open area. And these little hills are actually going to be helpful for us because we don't want to do what this is actually the highest resolution picture we have. So you can actually see the dunes. Okay. But even the dark areas that look smooth turn out to have little dunes in them. So, many years ago, in 1956, Chesley Bonestell, who's the father of space exploration art had imagined that we would land in an area like this where you'd have a nice view of some mountains that there would be little hills for you to drive up to. Here the rocket, this is a rocket plane scenario where the rocket is actually part of the airplane to the right when it lands on Mars, and then the central part of the airplane becomes erected into a rocket to return you to Earth. The rest of the plane with the wings stays on Mars. So that's sort of a hybrid type of design. Anyway, this was sort of a nice idea in the 1950s, but it doesn't make a lot of sense. As soon as a rocket takes off, that little dome-shaped base is going to get blown away by the rocket exhaust, and you don't have any protection there. So when I redid this painting, so to speak, humbly, but just with updates in the hardware, you know, I I show the landing and takeoff pad, the landing and launch pad, separated from the base where you would set up shop by little hills. And so you want to land in an area that's overall flat, but that has little hills. And this was a painting done in 2021. And sure, and then meanwhile, I don't see, can you see my cursor?
Yes.
And
Yeah, okay.
Pascal,
So,
this is me chiming in to say we're out of time for the hour.
okay.
So if you want to finish with this image.
Yeah, so the base is out there, but then the nuclear reactor that's powering the base is hiding behind a little hill. So you see that you really want to be in a place where you have all kinds of little hills to be properly set up. And this is why Krista's site is so beautiful, because it has these little hills. You can separate the landing pad and the launch pad of the rocket from the base and the nuclear reactor, in ways that are pretty easy. So I'll leave it at that. This is us imagining us driving onto the glacier with a volcano in the distance, with the salt deposits at the surface. That's it. Thank you.
Okay, well, that was quite an amazing tour of the whole topology of Mars around the Noctis site. Good work, Krista. I think it's exciting that she's going to get, oh, she's not here anymore. She's going to get to go talk about this at a conference coming up soon.
Yes. Yes.
Yes, so I think we still have our evaluation stuff to do. So
Okay.
please, students, stay with us. Everybody else can go.